Somewhere above your head tonight, just under 250,000 miles away, lies the farthest point any human being has ever physically touched. Not Mars, not Venus, not the outer planets, not even the empty dark between worlds. The Moon. That's it. That's the record. Set in December of 1972 and never broken since. Half a century has passed. Phones became supercomputers. Cars began driving themselves. We photographed a black hole from 93 million miles away, using light that left it long before any of us were born. And yet, not one human being has traveled farther from Earth than a small group of astronauts did during a handful of years in the late 1960s and early 1970s. Why? It is tempting to answer that question in a single sentence. Too expensive. Not enough political will. No good reason to go. And each of those answers contains a piece of the truth, but none of them explain the whole picture, because the real story is stranger, and in some ways more uncomfortable, than a simple lack of funding or ambition. The real story involves the human body breaking down in ways engineers never fully solved. It involves a form of radiation that space agencies still don't have a complete answer for. It involves a psychological unknown that no simulation on Earth can truly recreate. And it involves an economic and political machine that, once it got what it wanted from the Moon, quietly walked away from going any farther. Tonight we are going to take that question apart, piece by piece, and follow it wherever it leads. Because by the time we reach the end of this journey, the Apollo program will look less like the beginning of a new era of exploration, and more like a brief, extraordinary exception to a much harder rule. A rule written not by politicians, but by the universe itself. To understand why we stopped, we first need to understand what it actually took to go there in the first place. Apollo 11 left Earth on July 16, 1969, and reached the Moon just over 3 days later. From launch to splashdown, the entire mission lasted about 8 days. The astronauts spent barely more than 21 hours on the lunar surface itself. That number is worth sitting with for a moment, because it tells you something important. The Moon missions were not expeditions in the way we usually imagine them. They were closer to a sprint, a tightly choreographed dash to a nearby target, followed by an immediate return home. And even that short a trip pushed the technology, the biology, and the budget of an entire nation to their absolute limits. At its peak, the Apollo program consumed roughly 4% of the entire United States federal budget. 400,000 people across universities, private contractors, and government agencies worked on some piece of it. It required the invention of an entirely new class of rocket, a completely new form of guidance computer, and life support systems that had never existed before. All of that effort produced something remarkable. But it also produced something narrow. Apollo was built to answer one very specific question. Can we get a small number of people to the Moon and back safely, in the shortest possible amount of time? It was never built to answer a much harder question. Can we keep human beings alive, healthy and sane during a journey that lasts not 8 days but 8 months or longer? That question sat quietly in the background of the entire space race. Nobody had to answer it, because nobody was required to travel that far. The Moon was close enough that most of the deepest problems of long-duration spaceflight could simply be avoided rather than solved, which raises the real hidden question at the center of tonight's documentary. Was the Moon landing actually the first chapter of a longer story? Or was it something closer to the edge of what was ever truly achievable with the tools, the biology, and the political will available to us? To answer that, we need to look at what happens to the human body the moment it leaves the protective bubble Earth has quietly provided for billions of years. Right now, whether you realize it or not, you are standing inside one of the most effective protective systems in the known universe. Earth's magnetic field extends far beyond the planet's surface, forming an invisible barrier called the magnetosphere. It deflects the vast majority of charged particles streaming outward from the sun. Layered above that is the atmosphere itself, a blanket of gas roughly 60 miles thick that absorbs even more radiation before it ever reaches you. Together, these two systems make Earth's surface remarkably safe from a universe that is, in truth, extremely hostile to biological life. The astronauts who orbited Earth during most of NASA's missions, including the International Space Station crews of today, still benefit from a meaningful portion of this protection. The magnetosphere extends far enough that low Earth orbit remains relatively shielded. The Apollo astronauts were different. For a brief window measured in days, they left that shield behind entirely. And here is the detail that rarely makes it into the popular retelling of the moon landings. Those astronauts were lucky. In August of 1972, between the Apollo 16 and Apollo 17 missions, the Sun released one of the most powerful solar particle events ever recorded. Had astronauts been on their way to the moon during that window, the radiation dose they would have received could have been lethal, or close to it. They weren't there. The timing simply worked out. This is not a comfortable thing to say about one of humanity's greatest achievements, but it is true. The safety margin on radiation exposure during Apollo was thinner than most people realize, and it was never truly tested against a worst-case scenario. Now stretch that same exposure across a mission to Mars, a round trip to Mars, including the necessary waiting period for the planets to align correctly for the return journey, takes somewhere between 2 and 3 years using current propulsion technology. During that entire span, astronauts would be almost continuously exposed to two distinct radiation sources. The first is galactic cosmic radiation, a steady background rain of high-energy particles originating from exploded stars scattered across the galaxy. Unlike solar radiation, this type cannot be predicted or timed around. It is simply always there, at a low but constant level, quietly damaging cells and DNA over months and years. The second is the danger from solar events themselves. Unpredictable bursts capable of delivering, in a matter of hours, a radiation dose many times higher than what an Apollo astronaut received during their entire mission. Shielding against galactic cosmic radiation is a problem nobody has fully solved. The particles involved are so energetic that thick shielding can sometimes make things worse rather than better, because collisions between the incoming particles and the shielding material itself create a shower of secondary radiation, sometimes more dangerous than the original particle. This is not a minor engineering inconvenience. It is one of the central reasons a Mars mission remains, even today, partly a biological gamble rather than a purely technical achievement. Which brings us to a question worth pausing on. If the danger is real, if it is measurable, and if agencies like NASA and the European Space Agency openly acknowledge it in their own published research, why does the public conversation about space travel so rarely mention it? Part of the answer is that radiation damage doesn't look dramatic. There is no explosion, no visible failure, just an elevated, statistically calculated increase in the risk of cancer, cataracts, and damage to the central nervous system, appearing years or decades after the mission ends. It's a threat built for spreadsheets, not headlines. And it is only the first of several problems standing between humanity and any journey deeper into the solar system. The human body did not evolve in space. It evolved here, shaped over millions of years by a very specific, very constant force, pulling downward at all times. Take that force away, even temporarily, and the body begins responding almost immediately, in ways that reveal just how deeply gravity is woven into human biology. Astronauts aboard the International Space Station typically lose bone density at a rate of roughly 1 to 1.5% per month in weight-bearing bones, a rate comparable to, and in some cases faster than, the bone loss experienced by elderly patients with osteoporosis here on Earth. Muscle mass declines as well, particularly in the legs and back. The muscle's evolution, built specifically to fight gravity every waking moment. Exercise helps. Current space stations are equipped with specialized equipment designed to slow this decline. And astronauts spend roughly 2 hours a day using it. But slowing is not the same as stopping. And even with rigorous exercise routines, measurable loss still occurs. Now extend a mission from 6 months, the typical length of an ISS rotation, to 2 or 3 years, the realistic timeline for a Mars mission. The cumulative effect of that bone and muscle loss becomes a serious operational problem, not simply a long-term health concern. An astronaut arriving on Mars after a 6 or 7 month transit would need to function almost immediately in a gravity environment about 38% as strong as Earth's after months of near weightlessness. Simulations and existing physiological data suggest this transition could leave astronauts significantly weakened at precisely the moment they need to be at their most capable, deploying equipment, responding to unexpected problems, and simply staying upright and mobile in an unfamiliar and unforgiving environment. Bone and muscle are only part of the story. Fluid inside the body behaves differently without gravity pulling it downward. On Earth, blood and other fluids naturally pool toward the lower body throughout the day. In microgravity, that fluid shifts upward, toward the head and chest, causing a puffy-faced, thin-legged appearance nicknamed by some astronauts as puffy face, bird legs. That shift isn't just cosmetic. Researchers studying astronauts who spent extended periods aboard the space station discovered changes to the shape of the eyeball itself, along with swelling of the optic nerve, a condition now referred to as spaceflight-associated neuroocular syndrome. In some astronauts, these changes to vision did not fully reverse after returning to Earth. Nobody yet knows, with certainty, what happens to human eyesight, bone density, cardiovascular function, or immune response over a continuous exposure of 2 or 3 years, because nobody has ever been in space that long, continuously, without the safety net of a nearby return trip to Earth. The longest single continuous spaceflight in history, undertaken by Russian cosmonaut Valery Polyakov aboard the Mir space station in the 1990s, lasted just over 14 months. Polyakov's mission remains one of the most important data points scientists have for understanding the far edge of human endurance in space. A Mars mission would need to roughly double that duration, in a spacecraft smaller and more isolated than Mir ever was, without the possibility of a quick return if something went dangerously wrong. This is the quiet, unglamorous truth sitting underneath the entire question of why humans haven't gone past the moon. It isn't only about rockets. It is about whether a human body, shaped by billions of years of evolution under one specific gravitational force, can actually survive the deep unknown of that many months disconnected from it. If the body's challenges in deep space are measurable, at least in principle, the mind's challenges are far harder to pin down. Isolation research on Earth offers some clues, though never a perfect substitute. Antarctic research stations, submarine crews, and simulated Mars habitats like the High Seas project in Hawaii have all attempted to study what happens to human psychology under extended confinement with a small, unchanging group of people. The findings are consistent in one particular way. Somewhere around the midpoint of a long isolation period, a phenomenon researchers sometimes call the third quarter effect tends to appear. Motivation dips, irritability rises, small interpersonal frictions that would normally be forgotten begin to accumulate. Because there is no way to simply leave the room, take a walk outside, or spend an evening with someone new. Now imagine that same psychological pressure, except the crew isn't just isolated. They are approximately 14 light minutes from Earth at Mars's closest approach, and roughly 24 light minutes away at its farthest. A single exchange of messages, a question and its answer, could take anywhere from half an hour to nearly 50 minutes round trip. Real-time conversation with mission control becomes impossible. Astronauts would need to make significant decisions on their own in real time, without the reassurance of a voice from home guiding them through the moment. There is no calling for help and expecting an answer within minutes. There is only the crew, the spacecraft, and whatever training they carried with them. Add to that the view outside the window. During the months-long crossing to Mars, Earth itself gradually shrinks from a familiar blue marble into a barely visible point of light, and eventually disappears from naked eye view altogether. Some researchers who study the psychology of spaceflight have speculated about what they call the Earth out of view phenomenon, a hypothesized psychological shift that could occur once the home planet is no longer visible at all, something no human being has ever experienced, because no human being has ever traveled far enough for it to happen. Nobody knows exactly what that will feel like. Not really. Simulations can approximate isolation. They can approximate confinement. They cannot fully approximate genuine, physical remoteness, the true and total absence of Earth from the sky. This is one of the strange truths hiding underneath the surface of this documentary's title. We have sent robots past the moon, past Mars, past every planet in the solar system and beyond it entirely. But we have never sent a human mind that far from home, and we genuinely do not know, with complete confidence, how it will hold up. If you found yourself settling into this story, drifting along with these quiet, strange facts about what our bodies and minds can and cannot survive out there in the dark, you're always welcome to leave a like and subscribe so you don't miss the next journey we take together through the mysteries hiding just beyond our own night sky. Now, with that gentle piece of housekeeping behind us, let's return to the harder question waiting for us in the silence between the Earth and Mars. Because biology and psychology, as difficult as they are only two pieces of a much larger puzzle. Even if every biological and psychological hurdle could be solved tomorrow, there remains a purely physical wall standing in humanity's way, one that has nothing to do with courage or funding and everything to do with a stubborn mathematical relationship, first formalized by a Russian schoolteacher named Konstantin Tsiolkovsky at the turn of the 20th century. It's called the rocket equation, and it describes something deceptively simple. To accelerate a spacecraft to a given speed, you need fuel. But that fuel has mass, and accelerating that mass requires more fuel, which itself has mass, requiring still more fuel to move. The relationship isn't a straight line. It's exponential. Small increases in the amount of speed you need translate into dramatically larger amounts of propellant required to achieve it. This is part of why the Apollo missions worked, and why a Mars mission is a fundamentally different kind of challenge. Getting to the moon required escaping Earth's gravity and crossing 250,000 miles, an enormous achievement, but a comparatively short and well-understood hop within the Earth-Moon system. Getting to Mars means crossing tens of millions of miles at minimum through a transfer orbit that must be precisely timed to match the ever-shifting positions of two planets orbiting the Sun at different speeds. It means carrying enough fuel not only to get there, but ideally enough to return, or enough to produce fuel on the Martian surface using local resources, a technology still being tested rather than proven at scale. Every extra kilogram of food, water, radiation shielding, medical equipment, and backup systems needed to keep a crew alive for 2 to 3 years adds to the total mass that must be launched, accelerated, decelerated, and eventually landed. And under the rocket equation, mass is never free. It multiplies. This is one of the less glamorous reasons deep space missions have remained robotic for the past 50 years. A robotic probe doesn't need food. It doesn't need a pressurized cabin, a toilet, a gym to prevent bone loss, or redundant life support in case something fails. It can be lighter, cheaper, and dramatically less complicated, while still returning enormous amounts of scientific value. Voyager 1 and Voyager 2, launched in 1977, have now traveled farther than any human-made object in history, crossing the boundary of the solar system itself and entering interstellar space. They accomplished this using 1970s-era computer technology, a fraction of the budget of the Apollo program, and no human life at risk. That contrast, robotic missions quietly achieving one milestone after another, while human missions remain confined to low Earth orbit, and, once the Moon, is not a coincidence. It reflects a genuine, ongoing calculation happening inside every space agency on Earth. What can we learn? And at what cost? And at what risk? For robots, the answer has consistently been an enormous amount, cheaply and safely. For humans, the answer has remained far more complicated. It's worth returning for a moment to just how extraordinary the Apollo program actually was, because understanding its real achievement helps clarify exactly where the limits of that achievement lie. Apollo solved the problem of launching a vehicle capable of escaping Earth's gravity entirely, a feat that had never been accomplished with a crewed spacecraft before. It solved precision navigation across 250,000 miles of empty space, using guidance computers with less processing power than a modern digital wristwatch, an achievement that still impresses engineers today. It solved the problem of a controlled landing on another celestial body and a subsequent launch back off that body's surface, something that remains difficult even for robotic missions. Each of these was a genuine triumph of engineering, and each one deserves the reverence it still receives. But notice what all of these achievements share. They were solved for a mission lasting roughly a week, a mission where Earth remained close enough that, in a real emergency, trip could realistically be attempted within a matter of days, as demonstrated by the Apollo 13 mission in 1970, when an oxygen tank explosion forced the crew to abandon their lunar landing and rely on the lunar module as a lifeboat to survive the journey home. Apollo 13 is often remembered as NASA's finest hour, a triumph of improvisation and problem-solving under extreme pressure. It is less often discussed as evidence for just how fragile the entire system was and how much that fragility depended on the moon's proximity. The astronauts survived not only because of brilliant engineering on the ground, but because home was still, relatively speaking, close. A similar failure occurring 6 months into a Mars transit would not offer the same option. There would be no quick loop around a nearby body and a return within days. The nearest possible abort, depending on the specific mission architecture and the current alignment of the planets, could still mean months of additional travel through open space in a damaged or compromised vehicle, far beyond the reach of any rescue mission Earth could realistically launch in time. This is the quiet asymmetry sitting at the heart of Apollo's legacy. It proved that humans could survive a short, intense burst of deep space exposure, provided the destination was close enough for an emergency return. It never proved, because it was never designed to prove, that humans could survive true isolation, true distance, and a true absence of rescue options for years at a time. That distinction is not a criticism of the Apollo program. It is simply a reminder that the moon landing, remarkable as it was, answered a much narrower question than the one popular memory tends to assume it answered. And that narrower question is exactly why, after Apollo 17 splashed down in December of 1972, the story of deep human spaceflight didn't continue expanding outward. It stopped. To understand why humanity turned away from deeper exploration so soon after reaching the moon, it helps to remember what the Apollo program actually was. Underneath the science and the engineering, it was a geopolitical contest. The space race did not begin because of a widespread cultural passion for lunar science. It began in October of 1957, when the Soviet Union launched Sputnik, the first artificial satellite, and much of the American public reacted with genuine alarm. If the Soviets could put a satellite into orbit, many reasoned they could potentially deliver a nuclear weapon anywhere on Earth using similar rocket technology. Landing an American on the moon became, in that context, less about the moon itself and more about a very public demonstration of technological and ideological superiority during the Cold War. President John F. Kennedy's famous 1962 speech at Rice University made this explicit, framing the challenge as one the United States had to win, specifically because it was hard and specifically because winning it would demonstrate American capability to the entire watching world. Once Apollo 11 successfully landed in July of 1969, and the American flag was planted on the lunar surface with the world's cameras watching, the central political objective of the entire program had, in a very real sense, already been achieved. Everything after that point Apollo 12 through Apollo 17 was valuable scientifically, but politically, the mission had already succeeded. The budget numbers reflect this shift with striking clarity. NASA's funding, as the percentage of the federal budget, peaked around 1966, years before the actual landing, then began a steady decline that continued through the remaining Apollo missions and beyond. Apollo 18, 19, and 20, originally planned lunar missions, were cancelled outright, their hardware repurposed or placed in museums. This wasn't a failure of engineering. It was a shift in political priority. Once the symbolic victory had been secured, the enormous ongoing cost of continued deep space exploration became much harder to justify to a public and a Congress that had other, more immediate concerns competing for those same funds. From the Vietnam War to a growing list of domestic priorities. It's a pattern worth remembering, because it reveals something important about the true nature of Apollo's cancellation. Humanity didn't stop going to the moon because we discovered it was impossible to go farther. We stopped because the specific political conditions that made the enormous cost worthwhile in the first place had quietly disappeared. The technology didn't vanish. The rockets, at least in their basic design principles, still existed. What vanished was the singular, overwhelming national motivation required to spend 4% of a federal budget on something with no immediate military or economic return. And once that motivation faded, the harder biological and technical problems standing between the moon and Mars, the radiation, the bone loss, the isolation, the rocket equation, never had to be solved because nobody was urgently trying to solve them anymore. They simply sat there, unresolved, waiting. It would be inaccurate to say nothing happened in the decades between Apollo 17 and today. In truth, a tremendous amount happened. It simply happened in a very different direction than the public often expects. Through the 1970s and into the 2000s, space agencies around the world redirected the bulk of their human spaceflight efforts toward low Earth orbit. The Space Shuttle program, running from 1981 to 2011, never left low Earth orbit at all. The International Space Station, continuously inhabited since November of 2000, sits roughly 250 miles above Earth's surface, closer to the ground than many domestic commercial flights travel horizontally. This wasn't a step backward. It was, in a sense, the necessary next step nobody expected. Living and working in space long-term, understanding exactly how the human body degrades over months rather than days, testing life support systems that need to function reliably for years without a full resupply from Earth. Learning how small international crews cope with isolation and confinement. All of this research, quietly accumulating for over 2 decades aboard the ISS, has been building the actual scientific foundation that Apollo never had time to build. Meanwhile, robotic exploration continued, reaching farther and farther outward, largely unconstrained by any of the problems facing human missions. Viking landers reached Mars in 1976. Voyager 1 and 2 toured the outer planets throughout the late 1970s and 1980s before crossing into interstellar space decades later. The Galileo probe orbited Jupiter. Cassini spent 13 years studying Saturn. New Horizons flew past Pluto in 2015, sending back the first close images of a world so distant that its sunlight is roughly 1,000 times fainter than what reaches Earth. Each of these missions expanded human knowledge of the solar system enormously, and each one did so without requiring a single human body to survive the radiation, isolation, and physiological toll of the journey. It created an unusual and somewhat counterintuitive situation. Humanity's knowledge of the outer solar system grew by staggering leaps during exactly the same decades that human presence in space remained essentially frozen at the boundary of low Earth orbit. We know more about the surface of Pluto today than astronauts of the 1970s could have imagined possible. And yet, a human being still hasn't traveled farther than the moon. That gap between what we know and where we've physically been is, in many ways, the true hidden shape of this entire 50-year story. Robotic exploration solved the problem of learning about the solar system. It never solved, because it was never meant to solve, the much harder problem of sending a living human being safely through it. Chapter 9. The engines we still don't have. If you asked most people why humans haven't traveled past the moon, the first answer that comes to mind is usually rockets. Surely, the thinking goes, we simply haven't built anything powerful enough. The truth is more specific and more interesting than that. The Saturn V, the rocket that carried Apollo astronauts to the moon, remains one of the most powerful machines ever built by human hands. Chemical rockets like it work by burning propellant and expelling the resulting gas at extremely high speed out the back of the vehicle, generating thrust through simple, brute force physics first described by Isaac Newton. Chemical propulsion is reliable. It is well understood. It got 12 human beings to the lunar surface and back. But it has a hard ceiling on efficiency, measured in a value engineers call specific impulse. Essentially, a measurement of how much thrust you get from a given amount of fuel. For a trip to the moon, that ceiling was high enough. For a trip to Mars, it becomes a serious limitation, because a chemical rocket attempting the journey would need to carry an enormous mass of fuel simply to slow down and speed up multiple times across a voyage lasting many months, all while trying to keep the total mass of the spacecraft manageable under the unforgiving math of the rocket equation. This is why, for decades, engineers and researchers have been exploring alternatives, technologies that could make a Mars mission genuinely practical, rather than technically possible, but agonizingly slow and expensive. One promising direction is nuclear thermal propulsion, a technology that dates back, remarkably, to experiments conducted in the 1960s under a NASA and Atomic Energy Commission program called NERVA. Instead of burning chemical propellant, a nuclear thermal engine uses a small nuclear reactor to superheat a propellant, typically liquid hydrogen, and expel it through a nozzle. This approach can roughly double the efficiency of the best chemical engines, translating into shorter transit times and smaller required fuel loads. NERVA was actually tested successfully on the ground multiple times before being cancelled in 1972, the exact same year Apollo ended, for almost identical reasons. The budget and political urgency that justified the program simply evaporated once the moon race had been won. More than 50 years later, nuclear thermal propulsion is finally being seriously revisited. NASA and the Defense Advanced Research Projects Agency have been jointly developing a program called DRACO, intending to test a nuclear thermal rocket engine in orbit later this decade. It represents, in a very real sense, a technology humanity built once, shelved for half a century, and is now attempting to resurrect. Another approach, nuclear electric propulsion, uses a reactor to generate electricity that powers an ion or plasma engine, producing a much smaller amount of thrust than a chemical rocket, but sustaining that thrust continuously for months at a time. Over a long enough journey, this gentle, continuous push can outperform a single powerful chemical burn, gradually building up tremendous speed. Ion propulsion has already been used successfully on robotic missions, like NASA's Dawn spacecraft, which visited both the asteroid Vesta and the dwarf planet Ceres, using this exact technology, scaling it up to move a crewed spacecraft, along with all the mass required to keep a crew alive, remains an unsolved engineering challenge. There is a reason this matters far beyond simple curiosity about engine types. Every additional month spent in transit is another month of radiation exposure, another month of bone and muscle loss, another month of psychological isolation, another month where something could go wrong, far from any possibility of rescue. Faster propulsion doesn't just make a Mars mission more convenient. It directly reduces every single one of the biological and psychological risks discussed earlier in this documentary. In other words, the engine problem and the human body problem are not two separate obstacles standing in humanity's way. They are the same obstacle, viewed from two different angles. Solve propulsion sufficiently, and the radiation exposure shrinks. Solve it further, and the isolation period shrinks with it. This is part of why serious space agencies have stopped asking simply, can we build a rocket capable of reaching Mars? The Saturn V's descendants already could, given enough time and enough fuel. The real question has become, can we build a rocket fast enough and a spacecraft safe enough that the journey doesn't quietly kill or permanently damage the people making it? That is a fundamentally harder question, and it remains, even today, only partially answered. If Mars has always been the ultimate ambition, sitting behind humanity's spacefaring dreams, why did NASA's newest major human spaceflight program, Artemis, choose the Moon as its immediate destination, rather than aiming directly for the red planet? The answer connects almost every thread this documentary has pulled on so far. Artemis, named for the twin sister of Apollo in Greek mythology, aims to return American astronauts to the lunar surface and eventually establish a sustained human presence there, including a small space station orbiting the Moon called Gateway. On the surface, this can look like a step backward, retracing footsteps from half a century ago, rather than pushing outward toward genuinely new territory. But viewed through everything explored so far, it looks less like repetition and more like preparation. The Moon offers something Mars cannot: proximity, a journey that takes days rather than months, allowing engineers to test new life support systems, new spacesuits, new landing technologies, and new habitat designs, with a real emergency abort option still realistically available. It offers a genuine testing ground for the technologies a Mars mission will eventually depend on, without gambling astronaut lives across a 2 or 3 year commitment, with no easy way home if something fails. The lunar surface also offers a scientifically valuable target in its own right, one that Apollo barely began to explore. The lunar South Pole, where Artemis intends to land, contains permanently shadowed craters believed to harbor significant deposits of water ice, frozen for billions of years in regions of the Moon that never received direct sunlight. That ice represents a potential resource, not just for scientific study, but for practical use. Water can be split into hydrogen and oxygen, providing both breathable air and rocket propellant produced locally rather than launched at enormous cost from Earth. If humanity can learn to extract and use resources already present on another world, rather than hauling every gram of every necessity across the solar system, the entire mathematics of deep space exploration begins to shift. This concept, often called in situ resource or utilization, could eventually apply to Mars as well, where evidence of subsurface ice and even some liquid brine has been detected by robotic missions over the past 2 decades. In this light, the decision to return to the Moon first isn't hesitation. It's closer to due diligence, an attempt to solve, deliberately and carefully, exactly the kinds of problems Apollo's rushed timeline never had the chance to address. Radiation shielding for longer stays. Dust management. Since lunar dust proved sharply abrasive and surprisingly difficult to deal with during the original Apollo missions. Habitat systems designed to function reliably for months rather than days. There is also, underneath the engineering rationale, an echo of the same geopolitical pattern that shaped the original space race. China's National Space Agency has been steadily advancing its own lunar ambitions, including robotic sample return missions and a stated goal of landing Chinese astronauts on the Moon before the end of this decade, alongside a proposed international lunar research station developed jointly with Russia. Just as Sputnik once transformed American political will into a rapid, well-funded lunar program, the emergence of a genuine international competitor appears to be reintroducing some of that same urgency into Artemis today. Whether that renewed competitive pressure will prove sufficient to sustain the political funding for a subsequent Mars mission, in the way it once sustained Apollo, remains an open and genuinely uncertain question. History suggests political motivation for expensive space programs tends to be a fragile and temporary resource, easily present in moments of competition and easily withdrawn once the immediate goal, symbolic or otherwise, has been achieved. For most of the history described so far in this documentary, deep space ambitions have belonged almost entirely to national governments. That has begun to change, and the change matters more than it might initially appear. Private aerospace companies, most notably SpaceX, have introduced something the original space race never had: a profit-driven, iterative development approach, operating alongside, and sometimes ahead of, traditional government-led programs. SpaceX's Starship, a fully reusable spacecraft designed explicitly with Mars in mind from its earliest conceptual stages, represents a genuinely different philosophy toward deep space hardware. Rather than building a single, enormously expensive vehicle intended to work correctly on its first true mission, as Apollo largely had to, Starship has been developed through a rapid cycle of prototype testing, including a number of very public and very visible failures during early test flights. This approach carries real trade-offs. It generates dramatic footage of exploding test vehicles that can look, out of context, like failure, but it also allows for a pace of iteration. The traditional government contracting, with its lengthy design reviews and enormous individual mission costs, has historically struggled to match. Whether Starship or any privately developed vehicle will actually solve the deeper biological problems discussed throughout this documentary remains genuinely uncertain. A larger, more capable rocket does not, by itself, solve radiation exposure, bone density loss, or the psychological toll of isolation. It can, however, meaningfully reduce transit time, carry more shielding mass without prohibitive cost penalties, and support more redundant life support systems, addressing several of these problems indirectly through raw capability, rather than requiring an entirely separate physiological breakthrough. There is also a financial dimension worth acknowledging honestly. Ambitious public statements about crewed Mars missions arriving within a specific decade have circulated from private space companies for years now, and those specific timelines have consistently slipped. This is not necessarily evidence of dishonesty. Ambitious engineering timelines routinely slip across nearly every major technological undertaking in history. But it is a useful reminder that enthusiasm and genuine capability, while related, are not the same thing. What private spaceflight does appear to be changing is the underlying economic calculation. Government space programs have historically needed to justify enormous costs to elected officials, answerable to voters focused on more immediate concerns. Private companies, at least in theory, can pursue longer-term, higher-risk investments if they believe a future commercial return, whether through satellite launches, lunar resource extraction, or eventually crewed missions, justifies the expense. Whether that theory survives contact with the genuine difficulty of deep space human survival remains one of the most important open questions in this entire story. History has already shown quite clearly that a lack of political will was enough to end the last era of deep human exploration. It remains to be seen whether a new source of will, this time commercial rather than geopolitical, will prove any more durable. Despite everything described so far, decades of orbital research, renewed lunar ambitions, and a new generation of private spacecraft, it is worth being honest about exactly how much remains genuinely unknown. Consider radiation shielding. Current spacecraft designs rely largely on mass-thick material placed between astronauts and the harshest radiation sources to provide protection. But as mentioned earlier, sufficiently energetic particles can actually create secondary radiation when they strike shielding material, complicating the simple assumption that thicker is always safer. Some researchers have proposed alternative approaches, including active magnetic shielding that would generate an artificial magnetic field around a spacecraft, mimicking Earth's own natural protection on a small scale. This technology remains, even now, largely theoretical and untested at the scale a crewed mission would require. Consider artificial gravity. One proposed solution to the bone and muscle loss problem involves rotating a spacecraft, or a section of it, to generate centrifugal force that mimics gravity during the long transit to Mars. The physics behind this idea is well understood, dating back to concepts explored by engineers and scientists throughout the 20th century. But no crewed spacecraft has ever actually implemented a rotating habitat at meaningful scale, and questions remain about exactly how large such a structure would need to be to avoid uncomfortable side effects, like motion sickness, caused by the difference in centrifugal force between an astronaut's head and feet during rotation. Consider closed-loop life support. Current systems aboard the International Space Station recycle a significant portion of water and oxygen, but they still depend on periodic resupply missions from Earth for replacement parts, additional water, food, and other consumables. A Mars mission, roughly 2 to 3 years from launch to return with no possibility of resupply during transit, would require life support systems approaching near total closed-loop efficiency, recycling water, oxygen, and potentially even growing food at a reliability level that has never been demonstrated over that length of time in an actual spacecraft. Consider medical care. The ISS maintains regular communication with flight surgeons on the ground and, in a genuine emergency, can attempt a return to Earth within hours. A Mars crew experiencing a serious medical event, whether an injury, an infection, or a psychiatric crisis, would need to manage that situation with whatever training, equipment, and supplies they carried, potentially for months, without any possibility of evacuation. None of these problems are unsolvable in principle. Each one represents an active area of ongoing research, and meaningful progress continues to be made every year. But taken together, they explain why serious space agencies have generally resisted rushing directly toward a crewed Mars mission, despite the technology to attempt one, in some limited sense, already existing. The honest answer to why humans haven't traveled past the moon in 50 years is not a single dramatic obstacle. It is this accumulation of smaller, harder, less visually dramatic problems: radiation, bone density, isolation, life support reliability, propulsion efficiency, political will, each one individually manageable in short bursts, but collectively forming a wall that a week-long lunar mission never had to climb. It's worth pausing here to lay out, plainly and without exaggeration, what an actual crewed Mars mission would realistically require, based on current NASA and International Space Agency planning documents. A typical proposed mission architecture involves a transit of somewhere between 6 and 9 months to reach Mars, depending on the specific trajectory chosen and the alignment of the two planets at launch. Because Earth and Mars orbit the Sun at different speeds, the planets are only favorably aligned for an efficient transfer, roughly once every 26 months. Missing that window means waiting more than 2 years for the next opportunity. Once at Mars, because that same orbital alignment problem applies in reverse, a crew would likely need to remain on or near the planet for somewhere between several months and well over a year, waiting for Earth and Mars to realign favorably for the return journey. Total mission duration, from launch to splashdown back on Earth, would likely fall somewhere between 2 and 3 years. During that entire span, the crew would be exposed to continuous galactic cosmic radiation, punctuated by the ongoing risk of an unpredictable solar particle event. They would experience significant bone and muscle loss during the transit phases, followed by an abrupt and demanding readjustment to Martian gravity upon arrival, and eventually to Earth's gravity again upon return. They would be psychologically isolated from real-time contact with Earth for the majority of the mission, managing their own medical care, equipment failures, and interpersonal conflicts with minimal outside guidance. And they would be doing all of this in a spacecraft, and eventually a surface habitat, with essentially no possibility of rescue or evacuation if something went seriously wrong. This is not a description meant to suggest a Mars mission is impossible. Skilled, well-trained human beings have survived extraordinary circumstances before, and every individual problem described in this documentary has credible research pointing toward eventual solutions. It is, instead, meant to explain honestly why the gap between landing on the moon and landing on Mars is not simply a matter of building a bigger rocket and waiting for enough funding. It is a gap defined by duration, distance, and the absence of any safety net. Three factors that barely existed during Apollo's brief, carefully timed sprint to the nearest possible target beyond Earth. Understanding that gap doesn't diminish what Apollo achieved. If anything, it deepens the appreciation for it, revealing just how precisely engineered that narrow window of possibility actually was. The moon was reachable in 1969, using the technology and biological understanding available at the time, specifically because it was close enough to avoid nearly every problem discussed throughout this documentary. Mars is not yet. Despite the sobering picture painted across the last several chapters, it would be a mistake to end this documentary suggesting humanity has made no genuine progress towards solving these problems since 1972. The truth is closer to the opposite. Progress has been substantial, simply slower and less visually dramatic than a single triumphant mission broadcast to the entire world. Consider the accumulated total of human time spent in space since the end of Apollo. As of the mid-2020s, the International Space Station has been continuously inhabited for well over 2 decades, with astronauts and cosmonauts from more than 20 different countries cycling through 6-month rotations, generating an enormous, ongoing body of medical and physiological data that simply did not exist during the Apollo era. Every one of those rotations adds another data point to scientists' understanding of exactly how the human body responds to extended time in microgravity, gradually replacing educated guesses with genuine evidence. Consider NASA's twin study, published in 2019, which compared astronaut Scott Kelly, who spent nearly a year aboard the ISS, with his identical twin brother Mark Kelly, who remained on Earth throughout the same period. The study revealed measurable changes in gene expression, immune function, and even the length of protective structures on the ends of Kelly's chromosomes, called telomeres, some of which reversed after his return to Earth, and some of which did not. It remains one of the most detailed pieces of evidence humanity has ever gathered on the biological toll of extended spaceflight, and it simply could not have existed in the Apollo era, when no mission lasted anywhere close to long enough to generate this kind of data. Consider the steady advancement of radiation shielding research, propulsion technology once shelved for decades, and now actively being revived, and life support systems achieving recycling efficiencies that would have seemed remarkable to engineers working in the 1970s. None of this progress has produced a headline as dramatic as a flag being planted on another world. It has instead produced something quieter and, in its own way, more valuable. An accumulating foundation of genuine knowledge built specifically to answer questions Apollo never had the time, the funding, or the mission profile to ask. If humanity does eventually send astronauts to Mars, it will not be because someone finally decided to try something Apollo already proved was possible. It will be because someone finally finished solving the much longer, much harder list of problems. Apollo was fortunate enough to be small and fast, and lucky enough to avoid entirely. It's tempting, looking back across everything explored in this documentary, to feel a certain frustration. Surely, after 50 years, something so widely dreamed about should have happened by now. But there is another way to look at the same set of facts, one that reframes the entire story in a more accurate, and in some ways more remarkable, light. The universe was never designed to make this easy. Earth's atmosphere and magnetic field represent a genuinely rare and precious form of protection, built over billions of years of planetary history, and the moment any spacecraft leaves that protection behind, it enters an environment fundamentally hostile to the specific fragile biology that evolution happened to produce here. Distance in space is not measured casually. It is measured in months, in radiation doses, in the slow erosion of bone density, in the psychological weight of watching your home planet shrink into a point of light and vanish. None of this is a flaw in human engineering. It is simply the honest, unforgiving shape of the physical universe we happen to live inside. Viewed this way, the fact that 12 human beings ever walked on another world at all becomes something closer to a minor miracle than a modest first step. It required an extraordinary, almost unrepeatable alignment of political motivation, national wealth, technological timing, and, as the 1972 solar storm quietly reminds us, no small amount of luck. The 50 years since Apollo have not been an era of failure or stagnation. Despite how they are sometimes portrayed, they have been an era of quiet, unglamorous, essential preparation, humanity slowly building the actual knowledge, technology, and biological understanding that a week-long dash to the moon never required. We have not, in half a century, sent another human being farther than the moon. But we have, in that same half-century, come to understand exactly why that journey is so difficult, and exactly what it will take to finally make the next one. That understanding, incomplete as it remains, is not nothing. It may, in fact, be the necessary and unavoidable price of ever going farther at all. Long before the International Space Station existed, two earlier outposts quietly did much of the hard, dangerous work of teaching humanity what long-duration spaceflight actually costs. Skylab, America's first space station, hosted 3 crews between 1973 and 1974, the longest-lasting 84 days. That may sound modest compared to the year-long missions flown decades later, but at the time it represented uncharted territory. Skylab's astronauts experienced disorientation, motion sickness, and, in the case of the final crew, a level of scheduling pressure and fatigue significant enough that they eventually pushed back against mission control, requesting and receiving a day of genuine rest. It was a small moment, largely forgotten today, but it was also one of the first pieces of hard evidence that human endurance in space could not simply be scheduled around like an assembly line on Earth. The Soviet Union's Mir space station picked up where Skylab left off, operating from 1986 to 2001, and hosting, among many others, Valery Polyakov's record-setting 14-month mission mentioned earlier in this documentary. Mir also provided a far less comfortable set of lessons. A fire broke out aboard the station in 1997. A cargo vehicle collided with one of its modules the same year, depressurizing part of the station and forcing an emergency response from the crew. Life support systems failed repeatedly, requiring near-constant repair and improvisation from cosmonauts living, in some cases, for months inside an aging, increasingly fragile machine, held together as much by their own resourcefulness as by its original engineering. These were not failures in the way a rocket explosion is a failure. They were something more instructive. Evidence gathered the hard way of exactly how much can go wrong during extended time in space, and exactly how much resilience, repair capability, and calm decision-making a crew needs to survive it. The International Space Station, in many ways, was built on the scar tissue of these earlier programs. Its redundant systems, its emphasis on crew training for in-flight repairs, its international partnership structure, allowing continuous resupply from multiple countries, all trace back to hard lessons learned aboard Skylab and Mir. A Mars mission will, in turn, need to absorb everything the ISS has taught, particularly regarding a scenario neither Skylab nor Mir nor the ISS has ever truly had to face. A serious in-flight emergency occurring months away from any possible resupply or rescue. There is a temptation, when discussing the gap between the Moon and Mars, to treat it as an unprecedented problem, something entirely without historical parallel. It isn't, quite. Human history offers a handful of genuine parallels. Moments when explorers pushed toward a frontier that demanded not just courage, but the patient, decades-long accumulation of technology, medicine and logistics before it could be safely attempted. Consider the exploration of Antarctica. Early expeditions in the late 19th and early 20th centuries, including the famous and ultimately fatal journey of Robert Falcon Scott's team in 1912, revealed just how unforgiving extreme isolation, cold, and distance from resupply could be, even for extraordinarily well-prepared and courageous individuals. It took decades of subsequent advances in clothing technology, nutrition science, communication equipment, and transportation before permanent, safe, year-round scientific stations became possible on the continent. Today, researchers live and work in Antarctica routinely, in conditions that would have been lethal to the explorers of a century earlier. Not because courage increased, but because the supporting technology and medical understanding finally caught up to the ambition. Consider also the age of oceanic exploration, when sailing beyond sight of land for months at a time carried genuine, well-documented risks from scurvy, a disease caused by vitamin C deficiency that killed an estimated 2 million sailors between the 15th and 18th centuries, more than combat, storms, and shipwrecks combined. The solution, eventually discovered through careful observation and experimentation, was almost absurdly simple: citrus fruit. But it took centuries of trial, error, and countless preventable deaths before that connection was firmly established and adopted as standard practice. Spaceflight sits, right now, somewhere in the middle of a similar arc. The problems of radiation, bone loss, and isolation are the modern equivalent of scurvy and frostbite. Real, measurable, and not yet fully solved, but very likely solvable given enough patient research. The difference is that spaceflight, unlike sailing or Antarctic exploration, offers almost no opportunity for gradual, incremental real-world testing. A ship can turn back partway across an ocean. A polar expedition can retreat to a base camp. A spacecraft 6 months into a Mars transit has no equivalent option. That absence of a graceful retreat is in many ways the central historical novelty of this particular frontier, and it is precisely why space agencies have chosen to move as cautiously and deliberately as they have. However frustrating the caution might feel to those of us watching from Earth, eager for the next giant leap, it's worth returning, briefly, to the robotic missions that have quietly continued exploring the solar system throughout the decades since Apollo, because their success reveals something important about the actual balance of risk, cost, and scientific return currently shaping human spaceflight decisions. NASA's Perseverance rover, which landed on Mars in February of 2021, carries a small helicopter named Ingenuity, the first aircraft ever to achieve powered, controlled flight on another planet, originally intended to attempt just 5 short test flights. Ingenuity ultimately completed well over 70, providing aerial scouting data that helped guide Perseverance's exploration of an ancient river delta believed to have once carried water into a Martian crater billions of years ago. Perseverance itself has been collecting and sealing rock samples specifically chosen for eventual return to Earth, part of an ambitious multi-mission campaign called Mars Sample Return, involving a future lander, a small Mars ascent vehicle capable of launching samples off the planet's surface, and an orbiter designed to capture and carry them home. If successful, it will represent the first time material has ever been deliberately collected from the Martian surface and brought back to Earth for detailed laboratory analysis, offering scientists a level of detail no rover instrument, however sophisticated, can currently match. Meanwhile, the James Webb Space Telescope, positioned nearly 1 million miles from Earth, at a gravitationally stable point called the second Lagrange point, has been quietly transforming humanity's understanding of the universe far beyond the solar system, observing galaxies as they appeared more than 13 billion years ago, examining the atmospheres of planets orbiting distant stars, and doing so entirely without a single human being ever needing to travel anywhere near it after launch. Each of these missions underscores the same pattern that has defined the last 50 years. When the goal is knowledge, robotic and remote exploration has proven extraordinarily capable, often exceeding what a human crew could accomplish directly, at a fraction of the cost and none of the biological risk. This is not an argument against human exploration. Human beings bring adaptability, real-time judgment, and a form of hands-on scientific intuition that no current robot can fully replicate. Human missions to Mars would likely accomplish, in a matter of weeks, geological analysis that would take a rover like Perseverance years to complete. But it is a reminder that the decision to send humans farther than the moon has never simply been a question of whether it's possible. It has always also been a question of whether the scientific and symbolic value justifies a level of risk and cost that robotic missions simply do not carry. To make the abstract challenges of a Mars transit feel more concrete, it helps to imagine, briefly, what an ordinary day might actually look like for a crew somewhere in the middle of that journey, based on current mission planning concepts and lessons drawn from the International Space Station. The crew wakes on a schedule tied to Earth's 24-hour cycle, not because the spacecraft experiences day and night in any meaningful sense, but because human circadian rhythm, another biological system evolved specifically around Earth's rotation, still needs that structure to function. Breakfast comes from a carefully engineered supply of dehydrated and thermostabilized food, chosen for shelf stability across a mission lasting years rather than weeks, supplemented by whatever small amount of fresh food might be grown aboard using compact hydroponic systems, an area of active ongoing research aboard the ISS today. A significant portion of each day, likely 2 hours or more, is devoted to exercise using specialized resistance and cardiovascular equipment specifically designed to counteract the bone and muscle loss described earlier in this documentary. This isn't optional recreation. It is, quite literally, a medical necessity treated with the same seriousness as any other critical system aboard the spacecraft. Communication with mission control happens, but not in real time. A message sent to Earth might take anywhere from 10 to 20 minutes to arrive, depending on the spacecraft's exact position along its transfer orbit, with the reply taking another 10 to 20 minutes to return. Conversations, in the way we normally understand them, simply aren't possible. Instead, crews exchange longer, more deliberate messages, closer in spirit to letters than phone calls, a communication style that early long-duration ISS crews have already begun to describe in their own accounts of extended isolation. Maintenance work fills much of the remaining time, monitoring and repairing life support systems, checking radiation, shielding integrity, managing the spacecraft's navigation and power systems, alongside ongoing scientific research conducted during the transit itself. Free time exists, but it exists inside a volume of space roughly comparable to a small apartment, shared continuously with the same small group of people, for months at a stretch, with a window view offering for much of the journey. Nothing but stars and an increasingly small, pale dot that used to be home. It is, in other words, neither a dramatic emergency nor a glamorous adventure for most of its duration. It is closer to an extraordinarily demanding form of routine, sustained under conditions no human being has ever experienced for this long, this far from any possibility of return. Beneath the engineering and the biology sits a quieter, more uncomfortable question, one that space agencies have had to wrestle with directly rather than avoid. Who has the right to accept this level of risk, and on whose behalf? NASA maintains formal radiation exposure limits for its astronauts, calculated to keep the additional lifetime risk of fatal cancer from space flight-related radiation below a specific, carefully studied threshold. For missions confined to low Earth orbit, current technology and mission durations generally allow astronauts to stay safely within those limits across a normal career. A multi-year Mars mission, by contrast, could push an astronaut's cumulative radiation exposure close to, or in some proposed mission profiles beyond, the outer edge of what current guidelines consider acceptable, a genuine point of active debate among mission planners, medical researchers, and the astronaut corps itself. This raises questions that have no purely technical answer. Should agencies relax existing radiation limits specifically to make a Mars mission possible, effectively accepting a higher lifetime cancer risk for the astronauts involved than has ever previously been permitted? Should that decision be left entirely to the individual astronauts volunteering for the mission, fully informed, but ultimately choosing for themselves? Should there be an age requirement, given that older astronauts, statistically, have less remaining lifespan, during which a radiation-induced cancer might eventually develop? An ethically uncomfortable but scientifically logical consideration that has genuinely been discussed within space medicine circles. These are not questions engineers can solve with a better rocket. They are questions about how much risk a society is willing to knowingly ask a small number of its most skilled and dedicated people to accept, in pursuit of a goal that, however inspiring, offers no strategic military necessity and no guaranteed immediate practical return. The very absence of urgency that helped end the Apollo program in the first place. It's worth noting that every astronaut who has ever flown, from the original Mercury 7 to the crews currently rotating through the International Space Station has done so as an informed volunteer, fully aware, at least in general terms, of the risks involved. There is little reason to think a Mars crew would be selected any differently, but the scale of risk involved in a multi-year deep space mission, genuinely uncertain in ways low Earth orbit missions are not, means that whoever eventually accepts a seat aboard that first Mars-bound spacecraft will be doing something categorically different from anything any astronaut has agreed to before. It's worth briefly addressing a version of this story that often captures public imagination even more than the question of simply reaching Mars. The idea of humans not just visiting, but permanently living there. Colonization, in the sense often depicted in popular culture, self-sustaining cities under domes, generations of children born and raised on Martian soil, sits considerably farther along this same difficult road than even a single crewed visit. Everything discussed throughout this documentary regarding radiation, gravity, isolation, and life support applies not just to a 2 or 3 year mission, but multiplied across an indefinite, permanent stay. Martian gravity, at roughly 38% of Earth's, is an entirely unknown long-term environment for human physiology. Nobody knows, because nobody has ever experienced it, whether the human body can maintain adequate bone density, cardiovascular health, or normal fetal development across a full human lifespan, or across generations in that reduced gravity environment. Mars's atmosphere, less than 1% as dense as Earth's and composed overwhelmingly of carbon dioxide, offers no breathable air and minimal protection from radiation or micrometeorite impacts, meaning any permanent settlement would need to exist primarily underground or within heavily shielded structures for the foreseeable future. A far cry from the open, sunlit domed cities of science fiction. Proposals to terraform Mars, gradually thickening its atmosphere and warming its surface to become more Earth-like, do exist in serious scientific literature, but most current research suggests the process, even under optimistic assumptions, would likely require centuries or longer, using technology and resource extraction at a scale humanity has never previously attempted anywhere, let alone on another planet entirely. None of this means permanent settlement is impossible. It means, consistent with everything else this documentary has explored, that it sits considerably farther down a very long road than the more immediate, already difficult goal of simply sending a crew there and bringing them home safely. The dream of a self-sustaining Martian civilization is not the next step after solving the problems described in this documentary. It is, honestly, several steps beyond it, resting on top of achievements that haven't happened yet. Every individual challenge explored so far in this documentary, radiation, bone density, isolation, propulsion, cost, has its own dedicated community of researchers working on it, somewhere in the world. Often, with genuine measurable progress to show for their efforts. The harder, less discussed problem is what happens when all of these individually promising solutions need to work correctly. At the same time, aboard the same spacecraft, a nuclear thermal engine reduces transit time, which reduces radiation exposure and muscle loss, but it also introduces its own mass, its own safety requirements, and its own complications for emission architectures. Originally designed around chemical propulsion, better shielding material reduces galactic cosmic radiation exposure, but adds weight, the rocket equation punishes exponentially, potentially forcing a reduction in food, water, or medical supplies unless propulsion improves enough to compensate. A closed-loop life support system, reliable enough for 3 years, introduces new mechanical complexity, new potential failure points, in a spacecraft that already has no possibility of a resupply mission if a critical part breaks. This is sometimes called, within aerospace engineering circles, the systems integration problem, and it is arguably a more difficult challenge than any single technology described throughout this documentary. Improving one system in isolation is hard enough. Improving several systems simultaneously, while keeping the combined weight, power consumption, and failure risks within an acceptable overall envelope, is the kind of problem that consumes years of a mission architecture's development timeline, almost independent of how quickly any individual piece of underlying research advances. It's part of why NASA's Artemis program, and the Gateway station in particular, places such heavy emphasis on integrated testing rather than isolated laboratory experiments. A radiation shield that performs perfectly in a ground-based particle accelerator still needs to be tested attached to an actual spacecraft, drawing actual power alongside an actual life support system under actual mission conditions before anyone can responsibly certify it for a crew. This layered, compounding difficulty, where solving each individual piece only reveals how much harder it is to make all the pieces work together, may be the least visible and most persistently underestimated reason a Mars mission continues to sit years away, even as individual technologies described throughout this documentary keep steadily, genuinely improving. Buried in NASA's archives is a proposal that rarely makes it into popular retellings of the space race, one that offers a striking glimpse of just how differently things might have gone. In the early 1970s, engineers at NASA seriously studied a crewed flyby mission to Venus, intended to launch as early as 1973, reusing leftover Apollo and Skylab hardware. The plan involved a crew of 3 spending roughly a year in transit, swinging past Venus without landing, using the planet's gravity to help slingshot the spacecraft back toward Earth, gathering scientific data along the way. It never flew. Funding for it evaporated in the same wave of budget cuts that ended the later Apollo missions, and the planned Saturn V production line, another casualty of the fading political urgency described earlier in this documentary. What makes this foot worth revisiting is what it reveals. The raw hardware capability to send humans on a year-long deep space mission existed, at least in preliminary planning, remarkably close to the Apollo era itself. The obstacle was never purely technological. It has always, at every stage of this story, been a tangled combination of biology, economics, and political will, with the biological and economic pieces reinforcing each other in ways that are easy to overlook. Even if that Venus mission had flown, it would have run directly into the same unresolved radiation and physiological questions this documentary has spent so much time exploring. Likely with far less protective knowledge than researchers have accumulated in the half-century since. It might well have become one of the most dangerous and revealing experiments in the history of human spaceflight. Either a triumph that reshaped the following decades of exploration, or a tragedy that could have set the entire program back even further than the funding cuts eventually did. Its cancellation, in hindsight, may have been less a lost opportunity than an unplanned stroke of caution, sparing NASA from confronting the full weight of these unsolved problems decades before the research existed to properly address them. For thousands of years before any spacecraft existed, human beings still tracked Mars across the night sky, and the way that tracking evolved offers its own quiet lesson about patience and gradual understanding. Ancient Babylonian astronomers recorded Mars's motion with remarkable precision more than 2,000 years ago, noting its strange habit of appearing to reverse direction periodically against the background stars, a phenomenon now understood as retrograde motion, caused simply by Earth overtaking Mars in its faster orbit around the Sun. At the time, without that explanation available, the observation remained a genuine mystery, one that took centuries of careful, patient observation and mathematical refinement to finally resolve. Johannes Kepler, working in the early 17th century, spent years wrestling with Mars's orbital data specifically, eventually abandoning the assumption, held since antiquity, that planetary orbits had to be perfect circles. Mars's orbit, more elliptical than most other planets in the solar system, was stubborn enough, and the available data precise enough, thanks to decades of observations by his mentor Tycho Brahe, to finally force that old assumption to break. It became one of the pivotal moments in the entire history of science, and it happened specifically because Mars refused to fit the simpler picture astronomers had long assumed. There's a fitting symmetry in that history. Mars has always been the planet that resists easy answers, first forcing astronomers to abandon comfortable assumptions about the shape of the heavens, and now forcing space agencies to abandon comfortable assumptions about how quickly ambition alone can carry human beings across the solar system. In both cases, the eventual breakthroughs came not from a single dramatic leap, but from accumulated, patient observation, carried out over spans of time far longer than any one person's career. There's a deeper question quietly threaded through this entire documentary, one that space scientists refer to as the Fermi paradox, first articulated somewhat informally by physicist Enrico Fermi during a 1950 lunch conversation. Given the sheer number of stars in our galaxy, and the increasing evidence that planets are common around many of them, why has humanity never detected any confirmed sign of another technological civilization anywhere? There is no confirmed evidence. But among the many hypotheses researchers have proposed, one carries an uncomfortable relevance to everything explored tonight. Some scientists have suggested that interstellar travel, and perhaps even sustained travel across large distances within a single solar system, might be so biologically and technically demanding that most civilizations simply never manage to expand very far beyond their homeworld, regardless of how advanced their technology becomes in other respects. This documentary has spent considerable time detailing exactly why that difficulty is so persistent, even for a civilization as capable as our own. Radiation without a complete shielding solution, bone and muscle loss without a fully proven countermeasure, isolation without a true precedent. A rocket equation punishes distance exponentially. If these problems are genuinely difficult for humanity, an intelligent, technologically capable species with over half a century of dedicated spaceflight research behind it, they may be difficult in some form for any civilization anywhere in the universe attempting the same basic task, leaving home. It's worth being careful here. This is speculation, not established science, and it remains only one hypothesis among many attempting to explain the profound silence astronomers have observed across the galaxy. But it does offer a humbling perspective on the specific technical struggles detailed throughout this documentary. The gap between the Moon and Mars may not simply be a peculiar historical accident of 20th century American politics and budget cycles. It may be a genuine, physically grounded difficulty, one written into the basic relationship between biological life and the harsh, radiation-filled vacuum separating every world from every other world. If that's true, then every incremental piece of research described tonight, every radiation shielding experiment, every nuclear propulsion test, every year another astronaut spends aboard the International Space Station, isn't just solving a technical problem specific to Mars. It may be solving one of the genuinely fundamental challenges standing between life anywhere in the universe and stars above it. It's worth walking through in slightly more detail what NASA's current Artemis program actually intends to accomplish, step by step, because the sequencing itself reflects the patient, layered approach this documentary has argued is necessary. Artemis I, an uncrewed test flight launched in late 2022, sent an Orion capsule on a journey around the Moon and back, testing the heat shield, navigation systems, and overall spacecraft performance without risking a crew. A deliberately cautious first step, reminiscent of the uncrewed test flights that preceded the original Apollo missions. Artemis II, intended to carry a crew of 4 on a similar lunar flyby without landing, represents the first time humans will travel beyond low Earth orbit since Apollo 17 splashed down in December of 1972. And genuinely historic milestone in its own right, even though it involves no landing at all. Artemis III aims to finally return astronauts to the lunar surface, targeting the South Polar region, specifically because of its water ice deposits, using a lander derived from SpaceX's Starship program to carry the crew down from lunar orbit, a partnership between government mission planning and private spacecraft development that would have been almost unimaginable during the Apollo era's entirely government-run approach. Beyond that, NASA and its international partners envision a sustained lunar presence, including the Gateway Station in lunar orbit and eventually surface habitats capable of supporting longer stays, explicitly framed as a proving ground for the technologies, life support systems, and operational experience a Mars mission will eventually require. This layered structure, test flight, crowd flyby, crowd landing, sustained presence, deep space technology validation, mirrors almost exactly the patient, incremental approach this documentary has described as necessary throughout its exploration of radiation, biology, propulsion, and life support. It is a markedly different philosophy from Apollo's compressed, urgent timeline, trading the raw speed of a politically motivated sprint for the durability of a program built to actually survive changes in government, budget cycles, and public attention across the many years such research genuinely requires. Whether it succeeds in maintaining that durability remains, as with every chapter of this story, an open question. But the architecture itself, unlike anything attempted in the immediate aftermath of Apollo, appears designed specifically with the lessons of the last 50 years in mind. There is something worth returning to. Near the end of this journey, about the 12 human footprints still resting undisturbed on the lunar surface today, exactly as the Apollo astronauts left them, preserved by the moon's complete lack of wind or weather to erode them away. Those footprints are not evidence of a promise unfulfilled. They are evidence of an extraordinary, narrow, precisely timed achievement. One that happened to be possible under conditions unlikely to repeat themselves in quite the same way. A Cold War rivalry, urgent enough to fund an almost unthinkable expenditure. A destination just close enough to avoid the worst of the biological and physical problems described throughout this documentary. And, in the case of the 1972 solar storm, that never caught an Apollo crew mid-flight, a considerable amount of fortunate timing. 50 years of apparent stillness in deep human exploration have not actually been still at all. They have been filled with astronauts logging cumulative decades aboard space stations, physicians mapping exactly how bone density erodes and sometimes recovers, engineers reviving and refining propulsion technology first tested and then abandoned in the very same years Apollo ended, and mission planners designing, deliberately and patiently, a return to the moon meant not as a repetition of the past, but as a rehearsal for a future Apollo's rushed timeline never had the chance to prepare for. The next footprint, whenever and wherever it eventually lands, whether on the lunar South Pole within this decade or on the red dust of Mars sometime after, will not be a lucky accident. It will be the product of exactly the kind of unglamorous, incremental, sometimes frustratingly slow progress this documentary has spent so long describing. It is easy, looking back at Apollo, to focus entirely on the 12 men who walked on the moon. It is worth remembering, too, the much larger group who trained for missions that never happened, whose stories quietly illustrate just how abruptly the program's ambitions were cut short. Astronauts assigned to Apollo 18, 19, and 20, missions cancelled before they ever launched, had already begun geology training, already studied proposed landing sites more scientifically interesting than those actually visited, already prepared, in some cases for years, for journeys that were simply erased by a budget decision made in Washington. Harrison Schmitt, a professional geologist who eventually flew on Apollo 17, the final lunar mission, has spoken in later interviews about how differently the program's scientific return might have looked had those additional missions been allowed to proceed. Additional years of lunar samples, additional landing sites, additional data that instead simply never came to exist. This detail matters because it undercuts a comforting but inaccurate version of the story. The idea that Apollo ended naturally, its work essentially complete. It didn't. It ended abruptly, mid-stride, hardware already built and sitting unused, astronauts already trained and reassigned to other work, because the specific political conditions that had funded the program evaporated faster than anyone in 1969 might have predicted. Several of the Saturn V rockets, built for those cancelled missions, now sit non-functional as museum displays outside NASA facilities in Florida, Texas, and Alabama. Enormous machines capable, in principle, of doing exactly what this documentary has spent so long describing as difficult, quietly rusting as monuments to ambition outpaid by the willingness to keep paying for it. There is a particular kind of waiting embedded in every deep space mission that rarely gets discussed, outside specialist circles, one governed not by human patience, by the unforgiving arithmetic of orbital mechanics. Earth completes an orbit around the Sun in roughly 365 days. Mars, farther out and moving more slowly, takes approximately 687 days to complete the same journey. Because the two planets move at different speeds, their relative positions shift constantly, and only during a narrow window, approximately once every 26 months, do they align favorably enough for a spacecraft to travel between them using a reasonable amount of fuel along what's known as a Hohmann transfer orbit, the most fuel-efficient path between two orbits. First described mathematically by German engineer Walter Hohmann in 1925, decades before any spacecraft existed to actually use it. Miss that window, and the next opportunity isn't a matter of days or weeks. It's a wait of more than 2 years, an entirely different category of delay than anything encountered during the Apollo program, where lunar transfer windows occurred roughly once a month, offering considerable scheduling flexibility that a Mars mission simply does not have. This orbital rhythm shapes nearly every aspect of Mars mission planning discussed throughout this documentary. It determines when a crew must launch, how long they must remain at Mars, waiting for a return window, and how rigid the entire multi-year timeline becomes once committed to. There is no equivalent in ordinary human experience to a journey where missing a specific few weeks of readiness costs over 2 years of delay. A scheduling pressure that adds its own quiet, compounding stress to every other challenge this documentary has explored. Some proposed mission designs attempt to work around this constraint using what's called a free return trajectory or alternative transfer paths that trade efficiency for scheduling flexibility, but nearly all involve some combination of longer transit times, greater fuel requirements, or both, reinforcing yet again just how tightly every piece of this puzzle, propulsion, timing, biology, and cost remains interconnected. If there is a single number that captures why this documentary's central question has no simple answer, it may be this one: the estimated cost of a crewed Mars mission. According to various NASA and independent studies conducted over the past 2 decades, typically falls somewhere between $100 billion and $500 billion, depending on mission architecture, timeline, and how many of the technologies described throughout this documentary still need to be developed from scratch versus already existing. For comparison, the entire Apollo program, adjusted for inflation, cost the United States government approximately $150 to $280 billion in today's currency, spread across roughly a decade of sustained, politically motivated funding. A Mars mission, in other words, could easily cost as much as the entire Apollo program, concentrated not across the urgent 9-year sprint that followed Kennedy's 1962 speech, but across a much longer, slower timeline, without the same singular Cold War motivation driving Congress to approve it year after year. This is where the economics and the biology of this story tie back together in an uncomfortable knot. A faster, safer mission, one with better radiation shielding, more advanced propulsion, and more redundant life support, addressing exactly the problems described throughout this documentary, generally costs more to develop, not less. Cutting corners to save money tends to mean accepting greater risk in precisely the areas where this documentary has shown the margin for error to already be dangerously thin. Every space agency currently planning toward Mars is, in effect, walking a narrow path between two competing pressures. Spend enough to actually solve the radiation, gravity, and isolation problems detailed throughout tonight's journey, or spend less and accept a genuinely higher chance that something goes wrong. Far from any possibility of help, in a way, Apollo's shorter, closer missions were fortunate enough to never fully test. It's worth returning, near the end of this documentary, to the moon itself, because in the rush to discuss Mars, it can be easy to forget just how much of the moon Apollo actually left unexplored. The 6 Apollo landing sites that did fly were clustered largely near the lunar equator, chosen primarily for the relative ease and safety of landing there, rather than for their scientific richness. The lunar South Pole, Artemis's intended landing zone, was never visited by any Apollo mission, and its permanently shadowed craters, some of the coldest, darkest places anywhere in the solar system, having never received direct sunlight for potentially billions of years, remain almost entirely unexplored even today, studied only indirectly through orbital instruments aboard missions like NASA's Lunar Reconnaissance Orbiter. Those shadowed craters may contain not just water ice, but a kind of frozen historical record, ancient material deposited by comets and asteroids over billions of years, preserved by the extreme cold, in a way nothing on Earth's constantly changing, weathered surface ever could be. Some scientists have described these regions as a potential time capsule of the early solar system, an area of genuine ongoing scientific fascination, entirely independent of any future Mars ambitions. This detail reframes the return to the moon in a useful way. Artemis isn't simply a rehearsal for Mars, a stepping stone with no independent value of its own. It's also, quite genuinely, the first real opportunity to explore parts of our nearest celestial neighbor that Apollo's rushed, politically driven timeline never had the chance to visit, using instruments, geological training, and mission durations far more capable than anything available in the 1960s and 1970s. In that sense, the 50-year gap since Apollo hasn't just been about preparing for Mars. It's also been quietly an unfinished chapter of lunar exploration itself, one that Artemis is only now positioned to properly complete. One detail from the Apollo missions rarely receives the attention it deserves, and it offers a vivid, close-up illustration of just how thin the margin for error actually was, even during a mission as short and celebrated as a lunar landing. Lunar dust, unlike dust on Earth, has never been weathered by wind, water, or biological activity. It remains sharp, glassy, and abrasive at a microscopic level, the product of billions of years of micrometeorite bombardment grinding lunar rock into fine, jagged particles rather than the smoothed, rounded grains found in terrestrial soil. Apollo astronauts, working on the lunar surface for only a matter of hours across their missions, still found this dust clinging stubbornly to their spacesuits, working its way into joints and seals, and, once tracked back inside the lunar module, filling the cabin with a smell some astronauts compared to spent gunpowder. Eugene Cernan, commander of Apollo 17, later described how the abrasive dust damaged the outer layers of his spacesuit during his relatively brief time on the surface, and how engineers back on Earth expressed genuine concern about whether suits could have maintained their integrity across a longer mission, a future lunar mission lasting weeks rather than hours, or A Mars mission involving repeated surface excursions across many months would need to solve a problem Apollo barely had time to notice, let alone fully address, before its astronauts left the surface for good. This is a small, almost mundane detail compared to the grander challenges of radiation and propulsion discussed throughout this documentary, but it captures something important about the nature of deep space exploration. The universe doesn't just threaten astronauts with dramatic cinematic dangers. It threatens them with something as ordinary and unglamorous as dust, slowly compromising equipment never designed to endure prolonged exposure to an environment nothing on Earth adequately prepares for. Solving that problem, alongside every other challenge described tonight, is part of why current spacesuit designs being developed for Artemis missions incorporate dust-resistant materials and improved sealing systems, specifically informed by Apollo's hard-won first-hand experience, half a century after the fact. Attached to the Voyager spacecraft, but both still traveling outward through interstellar space today, is a golden record containing greetings in 55 languages, recordings of natural sounds from Earth, and a curated selection of music intended to represent something of human culture and experience, in case the spacecraft is ever encountered by another civilization. It was, in a very real sense, a message sent with no expectation of reply within any human lifetime, launched by a species that at the time had only just finished, proving it could send astronauts as far as its own moon. There's something quietly poignant in that timing, even as the political will to send humans farther than Earth's orbit was fading in the early 1970s. The same era that cancelled Apollo 18 through 20 and shelved the N-ERVA nuclear engine program, humanity was simultaneously launching Voyager's golden record outward, on a journey expected to outlast the sun itself. Still drifting through the galaxy long after Earth eventually becomes uninhabitable. It suggests that the impulse behind Apollo, the desire to reach outward, to be known, to leave some mark beyond the boundary of our own world, never actually disappeared when the funding did. It simply redirected itself from the expensive, biologically demanding project of sending humans toward the comparatively inexpensive, technologically simpler project of sending our machines and a small, carefully chosen record of who we are in our place. Voyager 1, as of the mid-2020s, remains the most distant human-made object ever created, still transmitting a faint signal back to Earth, using a transmitter with less power than a refrigerator light bulb. More than 15 billion miles from home, it has, in its own quiet way, already gone farther than any human being ever has, or quite possibly ever will, in the lifetime of anyone alive today. It's worth considering, briefly, who exactly will be responsible for finally closing the gap this documentary has spent so long describing. Unlike the Apollo era, when a relatively small, centralized group of government engineers and a handful of political leaders effectively controlled the entire pace and direction of human deep space ambition, today's landscape is considerably more distributed. NASA and its international partners, including the European Space Agency, Japan's JAXA, and the Canadian Space Agency, continue to drive much of the scientific and engineering research described throughout this documentary. China's national space program has emerged as a genuine, independent center of lunar and eventually Martian ambition, operating largely outside the cooperative framework the United States and its traditional partners maintain. And private companies, particularly SpaceX, have introduced an entirely new source of funding, ambition, and technological iteration that didn't meaningfully exist during the original space race at all. This diffusion of effort carries both risks and advantages. On one hand, it means the entire enterprise of deep space exploration no longer depends on a single government's shifting political priorities, the way Apollo's continuation once did, when a change in Cold War urgency alone was enough to end the program. Multiple, independently motivated efforts increase the overall odds that at least one of them sustains the multi-decade commitment this documentary has argued is genuinely necessary. On the other hand, it introduces new coordination challenges. Questions about international law under the Outer Space Treaty of 1967, which prohibits any nation from claiming sovereignty over celestial bodies, but says considerably less about the rights of private companies operating there. Questions about shared safety standards and questions about whether competition between these various efforts will accelerate genuine progress or simply duplicate the same expensive, difficult research multiple times over, rather than sharing it collaboratively. Whoever eventually sends the first crew past the moon, whether a national space agency, an international partnership, or a private company operating under a government contract, will be inheriting every piece of research, every hard lesson, and every incremental achievement described throughout this documentary. A foundation Apollo's astronauts never had the luxury of standing on, because they were the ones building it for the very first time. For all the difficulty described throughout this documentary, it's worth pausing to appreciate something remarkable hiding inside the same research that reveals these problems. The human body, for all its evolutionary attachment to Earth's specific gravity and atmosphere, has proven far more adaptable than early spaceflight pioneers had any right to expect. When Yuri Gagarin became the first human in space in 1961, spending just under 2 hours in orbit, doctors on the ground genuinely worried whether a human being could swallow, think clearly, or maintain basic bodily function at all in weightlessness, concerns that seem almost quaint in hindsight, but were entirely reasonable, given how little was known at the time. Gagarin's uneventful flight, medically speaking, was itself a significant scientific finding, quietly proving that at least the most immediate, catastrophic fears about spaceflight's effect on the human body were unfounded. In the decades since, astronauts have not simply survived extended time in space. Many have described a genuine physical and sensory adaptation, an increasing comfort with movement in 3 dimensions, a recalibration of balance and spatial awareness, even changes in how the brain processes visual information without a consistent down to orient itself against. Scott Kelly, during his nearly year-long mission aboard the ISS, described in interviews how his body gradually adjusted to microgravity in ways that made the final months noticeably more comfortable than the disorienting early days. This adaptability doesn't erase the serious risks documented throughout this journey. The bone loss, the radiation exposure, the vision changes some astronauts never fully recover from. But it does complicate any purely pessimistic reading of the story. The same biology that makes deep space travel dangerous has also, repeatedly, demonstrated a genuine capacity to adjust, compensate, and endure conditions evolution never specifically prepared it for. offering a real evidence-based reason for cautious optimism, alongside the documentary's more sobering findings. It is, in its own way, one of the more quietly hopeful threads running underneath everything else explored tonight. The problems are real, but so, repeatedly, is the body's capacity to meet them partway. It's worth returning, in a bit more detail, to the gateway station currently being developed as part of the Artemis program, because its specific design choices reveal exactly how deliberately mission planners have been working to address the problems described throughout this documentary. Unlike the International Space Station, which orbits Earth at a relatively low, well-protected altitude, Gateway will orbit the Moon in what's called a near-rectilinear halo orbit, a stable, fuel-efficient path that brings it relatively close to the lunar surface at some points and much farther away at others. This orbit was chosen specifically because it offers reliable, continuous communication with both Earth and the lunar surface, while requiring minimal fuel to maintain, an important consideration given everything this documentary has explained about the punishing mathematics of the rocket equation. More importantly, Gateway will exist substantially outside Earth's protective magnetosphere, exposing it and any crew aboard it to a level of galactic cosmic radiation much closer to what a Mars-bound crew would actually experience than anything the International Space Station's astronauts currently encounter. This makes Gateway, quite deliberately, a genuine radiation research platform, an opportunity to test shielding technologies and gather physiological data in an environment that finally, honestly resembles the deep space condition this documentary has spent so much time describing as unsolved. Gateway will also serve as a staging point for lunar surface missions, and eventually, mission planners hope, as a proving ground for life support and habitat technologies intended for eventual use on the far longer journey to Mars. It represents, in miniature, almost every theme this documentary has explored. An attempt to gather real data on radiation, a testbed for technologies rather than a symbolic destination in itself, and a deliberately patient, incremental step rather than a rushed, politically motivated sprint, where the Gateway succeeds in providing the specific data needed to finally close the radiation and life support gaps described throughout tonight's journey remains to be seen. But its very existence reflects a space agency that has, after 50 years, genuinely internalized the lesson at the heart of this documentary. The distance between the Moon and Mars cannot be closed by ambition alone. Even as this documentary has focused heavily on the obstacles standing between humanity and Mars, it's worth remembering just how much robotic exploration has revealed about the planet itself, discoveries that continue to reshape exactly what a future human mission would actually find waiting there. For most of the 20th century, Mars was widely assumed to be an essentially dead world, geologically inactive and entirely dry. Its reddish surface, simply an ancient, unchanging desert. That picture has changed dramatically over the past 2 decades. Orbital radar data, gathered by the European Space Agency's Mars Express mission, suggested the possible presence of a liquid water lake beneath the planet's south polar ice cap, kept unfrozen by a combination of pressure and dissolved salts. Though the finding remains debated among planetary scientists and has not been definitively confirmed. NASA's Curiosity rover, exploring Gale Crater since 2012, has detected seasonal fluctuations in methane concentrations in the Martian atmosphere, a finding that remains unexplained and could, in principle, though far from certainly, be connected to either geological activity or, more speculatively, biological processes. Mars also turns out to be far more geologically active than once assumed. NASA's InSight lander, which operated on the Martian surface from 2018 to 2022, detected hundreds of Marsquakes using an extraordinarily sensitive seismometer, revealing a planet with an active, if much quieter, geological interior than Earth's. Information that helps scientists understand not just Mars, but the early formation of rocky planets throughout the solar system, since Mars, smaller and cooler than Earth, effectively preserves geological conditions similar to what our own planet may have experienced billions of years ago. These discoveries matter for reasons beyond pure scientific curiosity. A future human crew studying Mars directly, with the kind of hands-on geological expertise that Apollo astronaut and trained geologist Harrison Schmitt brought to the lunar surface, could investigate these mysteries with a speed and adaptability no rover, however sophisticated, has yet matched. The question of ancient or even present Martian life, one of the most profound questions science could possibly answer, may ultimately require exactly the kind of nuanced, real-time judgment that only a human geologist standing on the Martian surface, sample in hand, can truly provide. It's a reminder that everything this documentary has described as an obstacle, radiation, isolation, propulsion, cost, exists specifically because the destination on the other side of it remains so genuinely, scientifically extraordinary. Spaceflight is not the only field of modern science forced to operate on a timescale that outlasts any single funding cycle, and looking briefly at its neighbors offers a useful sense of scale for just how ordinary this kind of extended timeline actually is, outside the specific frustration of watching it apply to something as exciting as Mars. The International Thermonuclear Experimental Reactor, an enormous fusion energy project under construction in southern France, through a partnership of 35 countries, was first formally proposed in the mid-1980s. Ground was broken in 2010. The facility is not expected to begin full-scale deuterium-tritium fusion experiments until sometime in the 2030s, meaning the entire arc from serious proposal to genuine operational result spans roughly half a century, almost precisely matching the gap this documentary has spent so long examining. The Human Genome Project, an effort to map the complete sequence of human DNA, took 13 years from its formal 1990 launch to its completed draft in 2003, a project many participating scientists initially assumed might be finished within a much shorter window, only to discover the underlying biochemistry was considerably more intricate than early estimates allowed for, a pattern that will sound familiar to anyone who has followed the steadily lengthening timelines of nuclear propulsion research or radiation shielding development, described earlier in this documentary. Even the search for gravitational waves, ripples in spacetime first predicted by Einstein in 1916, took almost exactly a century to confirm, requiring detector technology sensitive enough to measure distortions smaller than a fraction of the width of a proton, technology that simply did not exist for most of that intervening century, and had to be built, tested, and refined across generations of physicists who would never personally witness the eventual 2015 detection. None of these examples make the 50-year gap since Apollo feel shorter, but they do suggest that the particular shape of this story, an early dramatic breakthrough followed by decades of quieter, harder groundwork before the next major leap becomes possible, is less an anomaly specific to space exploration and more a recurring pattern across nearly every field of science attempting something genuinely at the edge of what current technology and understanding allow. Long before any spacecraft leaves Earth-bound for Mars, its exact path will already have been calculated, tested, and refined for years, an aspect of deep space travel that highlights just how much of this entire endeavor depends on getting the invisible mathematics right long before the visible engineering ever begins. Modern trajectory design relies on decades of accumulated tracking data for both Earth and Mars, refined continuously by every prior mission that has ever measured the two planets' positions with increasing precision. Even tiny errors in that data, errors of a few kilometers across a journey spanning tens of millions of miles, can compound into significant deviations by the time a spacecraft actually arrives, which is why robotic Mars missions routinely perform small course correction burns throughout their transit, nudging their trajectory gradually rather than attempting a single perfect launch. A crewed mission would carry this same requirement, but with dramatically less room for error. A robotic probe that misses its intended landing zone by a few miles can often still function successfully elsewhere on the Martian surface. A crewed spacecraft that arrives even slightly off course, particularly during the delicate entry, descent, and landing sequence that has destroyed a significant number of robotic Mars missions over the decades, could face consequences with no acceptable margin for improvisation. This is part of why entry, descent, and landing, a sequence engineers sometimes only half-jokingly refer to as the 7 minutes of terror. Given how little real-time control is possible, once the spacecraft begins its final descent through Mars's thin, unpredictable atmosphere, remains one of the most closely studied and refined aspects of Mars mission planning today. Perseverance's successful 2021 landing using an innovative sky crane system that lowered the rover gently to the surface on cables from a hovering rocket-powered platform represents the most advanced version of this technology yet flown. And even it carried genuine, acknowledged risk of failure right up until the moment it succeeded. A crewed landing system will need to exceed even that level of reliability, a requirement that continues to shape spacecraft design work happening right now in the laboratories most of the public will never see, years before any human crew is scheduled to depend on it. There is a particular kind of resolve required to sustain a 50-year effort toward a goal that offers no guaranteed timeline, no certain success, and no dramatic yearly milestone comparable to a lunar landing broadcast to the entire world. It would be easy to mistake this long, patient middle chapter of the story for stagnation, for a species that simply lost its nerve after the triumph of Apollo. Everything explored throughout this documentary suggests a different, more accurate reading. The nerve was never really the missing ingredient. The missing ingredient was time. The decades genuinely required to gather physiological data no simulation could substitute for, to revive and refine propulsion, technology shelved in a moment of premature budget cutting, to build the kind of durable, internationally distributed effort capable of surviving changes in government far better than a single nation's Cold War urgency ever could. There's a specific psychological cost to this kind of waiting that rarely gets discussed openly within space agencies themselves, but occasionally surfaces in interviews with the scientists and engineers who have spent entire careers on pieces of this puzzle. Many of the physicians currently studying astronaut bone density aboard the ISS will likely retire before a Mars mission ever launches. Many of the engineers refining nuclear thermal engine designs today are working on a technology whose first genuine deep space test may not occur until well into their children's careers, not their own. This is, in a very real sense, a multi-generational scientific relay race, where individual researchers contribute a leg of the journey they may never personally see completed, trusting that the next generation will carry the baton forward using exactly the data, the failures, and the incremental successes they leave behind. 50 years is a long time by the measure of a single human career. It is a remarkably short time by the measure of the problem actually being solved, one that requires literally decades of continuous in-orbit study simply to begin answering with confidence. The next chapter of this story, whenever it finally arrives, will belong to researchers who, in many cases, have not yet begun their careers, inheriting a foundation built by people who spent their working lives on a goal they knew, going in, they might never personally witness. So here is where this journey leaves us. The real reason humans haven't traveled past the moon in over 50 years is not any single obstacle. It is not simply a lack of funding, though funding matters enormously. It is not simply a lack of political will, though that too has clearly played its part. It is not simply a matter of insufficiently powerful rockets, though propulsion technology remains an active area of necessary progress. It is the quiet, cumulative weight of radiation exposure without a complete shielding solution, bone and muscle loss without a fully proven countermeasure, psychological isolation without a true historical precedent to draw from, a rocket equation that punishes every extra kilogram of the food, water, and safety equipment a multi-year mission would require, and a political and economic system that, once it achieved its original symbolic goal on the lunar surface, quietly withdrew the extraordinary, unsustainable level of resources that goal had temporarily commanded. Apollo did not fail to continue outward because humanity lost its courage or lost interest in the stars. It stopped because the very specific, narrow set of conditions that made it possible in the first place, a close destination, a short mission, an overwhelming and temporary political motivation, was never actually sufficient to carry humanity any farther than it did. Going to Mars, or beyond, will require something Apollo never needed: patience. The slow, decades-long accumulation of exactly the kind of unglamorous research currently happening aboard the International Space Station, in nuclear propulsion laboratories, in radiation shielding experiments, and in the quiet planning documents of Artemis, all of it building, piece by piece, toward a mission that Apollo's rushed, brilliant, lucky sprint to the moon was never designed to attempt. We began this documentary standing beneath a familiar moon, wondering why it remains the farthest point any human being has ever reached. We end it with a somewhat different understanding. The moon isn't the limit of human ambition. It was always going to be the first step. What nobody fully appreciated in 1969 was just how large how demanding, and how unforgiving the space between that first step and the next one would actually turn out to be. Somewhere right now, engineers are quietly testing a new generation of nuclear rocket engines. Physicians are studying astronaut bone density data collected over decades aboard the ISS. Mission planners are mapping out lunar habitat, designed specifically to rehearse the technologies a Mars crew will eventually depend on. The next footprint beyond the Moon has not been placed yet, but for the first time since 1972, it is finally, quietly, being prepared for. And when it finally happens, whenever that turns out to be, it will not be the result of a sudden burst of political urgency, the way Apollo was. It will be the result of exactly what this documentary has spent the last 2 hours describing. The slow, patient, unglamorous work of finally solving every quiet problem the Moon was simply too close and too brief a destination to ever force us to confront.